Hello everyone. In two of my previous videos on machine learning, you have seen me talking about the methods that are called value-based. So they try to approximate the return by some values, right? Like Q values, for instance, and then using those, they can basically find the good policy, the optimal policy. So those are called value-based function. We learned the Q-learning, which was off policy, and we learned the SARSA, which was on policy. Now in this video, we are going to look at the other category of reinforcement learning methods called policy-based. And one of the earliest ones is called reinforce. So let's get to it. The major difference between policy-based and the previous ones, value-based, is that the policy-based, they directly learn the policy that maps the states to actions. They do not need to have these estimates, which we call value functions, okay? Whether a state value function or a state action value functions, those V's or Q's, they don't need that. They directly learn the policy, okay? So their goal is to directly find the optimal policy, pi of theta of A given S. Now, the important thing is this. These policies, they have some parameters that you can adjust, okay? Theta is the learnable parameter of the policy, and the goal is to change this theta so you can maximum some expected return, okay? So here, these functions have some parameters in them, not like previous cases that they were either deterministic or stochastic, but there was no parameter. So when are these policy-based methods used? They can be used for environments that are continuous. They can be dealing with stochastic action spaces. They can be dealing with high dimensional policies, like when you're using neural networks to approximate functions. They can be used for partially observable, basically Markov decision processes, and they can work around stability issues that some of the value-based methods had, like Q-learning. Now the reinforce that we're gonna see, that's like the very basic of them. So it's not free of issues and so on. Okay, it has some issues, disadvantages, which we'll get to it at the end. So this was like the one of the very first ones, one of the basic ones. And then over time, they improved on that and they got better. So the first thing is, of course, if you want to have a theta change, you want to have a cost function, an objective function as a function of theta that you want to minimize or maximize. So in this case, what you want to maximize is the expected return after the initial state or the start state. This is what you want to maximize as your cost function. So this is the expected return under policy pi of theta of what? Of R of t. And R of t here is, as you can see, the cumulative return starting from state 0 all the way to the last state. And here you see all of the immediate rewards are discounted, right? Of course, for t of 0, it's not, but any t after that, you have a power of gamma to it. And this tau that you see here, this is your trajectory. This is the trajectory of like S naught, A naught, R1, S1, A1, R2, and so on. So you start in a state, you followed the policy, you took an action, that gave you a reward, that also landed you in state S1. Again, you followed the policy, you went for A1, you got R2 and went all the way to the last state, which is, for instance, like your goal state or something. So all of this, if we put it under trajectory tau, then the return for this trajectory tau, the cumulative return, is what we want the expected value of it to be maximized when my trajectory is being formed with policy pi. Okay? And another way to write it, because this is expected policy and these could be discrete or continuous states, let's say in this case a discrete state, right, of only a few number of transitions, then you can say summation over the trajectory of pi of tau given theta and r of tau. And so this is that entity that you wanted to maximize, and P here is a probability. Probability of what? Probability of the trajectory. Okay, which is of course under policy pi of theta. So if you multiply the function by the probability of that trajectory, then that is going to be of course the expected value. So this is my cost function. My goal is to change theta so that we can maximize j of theta. Now, how do we do it? Well, here we use the gradient methods, right? Like steepest descent, in this case, the steepest ascent, right? So we have to move in the positive gradient direction to maximize the function. So the important thing is to find the gradient of this j. If I can find del of j with respect to theta, right? So partial of j with respect to theta, then that is basically what I can use to go in a, as I said, steepest ascent algorithm like this, where each theta is added to that gradient multiplied by a learning rate. And this is, as I said, this is like the steepest ascent, as opposed to steepest descent that you have when what that was used for minimizing a function. This is for maximizing. You see here I'm using in the positive gradient. If it was negative, that would be steepest descent. So now the question is, what is this gradient? How do we calculate that? Okay, so that is the main thing that we need to calculate. Now here it says that the gradient of the cost function will be expected value of summation of t goes from 0 to t, from beginning to end, of gradient of log of the policy times r of t, where here r of t is basically the return that you have starting from time t all the way to the end of the time. And clearly for time of 0, that is from 0 to the last part. From t of 1 is from 1 to the last part. So it says if you have this policy function, take a log of that and take a gradient of that multiplied by these cumulative rewards starting from time t, sum them up, expected value of that is your gradient. Now the question is, well, where did you get that, right? So yeah, that's the gradient. That's how steepest descent, the reinforced method works. Yes, but show me why, right? Where does that come from? Because in engineering and in data science or mathematics and physics, we don't want to just accept something because somebody says so, okay? You always want to see why. Where does the derivation come from? So this is the derivation. Let's go over that. So here, let's assume that the policy is pi of theta of a given s. Fine. And the transition function is p of s prime given s and a, right? So s prime is the new state. Okay, so p of t and theta, this probability of the trajectory, which we just talked about here, how can we write that? It is going to be the initial probability, the probability of being in the initial state, times multiplication from t of 0 to t minus 1 of the policy times the transition function, correct? So if we have a transition function and this takes us from state st to st plus 1, and the action at from st is taken from the policy, and you started from row of s0, assuming that these back-to-back things are only determined by the policy, then a product like this would do the job, correct? Because you started with some initial chance, and then under some policy, which itself is probabilistic, now you took some action, like for instance A0 given S0, and then now that you took A0 and you only had so much chance of taking A0, because in this algorithm you can also do exploration, then now what is the chance that when you took action A and you were in state S, you end up in S plus 1? Most of the time it could be 100%, but not always, okay? So if you do a simple grid search problem and the navigation, this is kind of 100%, but not always we have 100% of transition. So now this is that probability, and now with this new probability, hopefully with state S0 and action A0, I can end up in S1. And again, with another probability, I can take action A1, and then hopefully with another probability of transition, I end up in state S2, and so on and so forth. So you see all of these initial and subsequent probabilities, they have to be multiplied together to give you the probability of going through the track of all of these S1, S2, S3, and A1, A2, A3. Okay, so we just multiply them together. This is like stuff that are independent from each other. So now what? That is the transition probability that I needed right here. Okay, so I could formulate that part. R of t is also formulated. So based on that, I can have an idea of my cost function, and now I can start taking gradient of that. So now I'll take a gradient of this. So I plug this equation 2 right into equation 1, as I said, and bring this definition of R of t. So 1 is going to be a good function of j. And now from j, I take a gradient. So I get gradient of j equals. Now, what would you get? It is going to be the gradient of summation over tau of p of t, r of t, correct? That's just applying a gradient to equation 1. That's all it is. If you look at it, all I did, I applied a del to both sides of this. And now, here, know that this is derivative with respect to theta, right? And this is summation over the trajectory, so I can take this del theta inside the summation and write it like that. Okay, that's the same thing. Now, the thing is, this guy has nothing to do with theta, this cumulative rebarb. It's this transition probability that has theta in it. Where does it have theta in it? It has theta in these parts. Okay, in these pies, this is where the thetas are showing up, and that is where you take those derivatives. Now here we do one small algebraic manipulation called the log derivative trick. Okay, and it's by trick here we are talking about an algebra basically. It says that the gradient of p can be written as p times gradient of log of p. And you know this is true. Why? Because, for instance, if I say d over dx of y is the same as y times d over dx of natural log of y. By the way, here when we say log, we are talking about natural log. So what's the x derivative of natural log of y? You know this is going to be d of y over dx over the y itself, right? And guess what? Now you can cancel this y and this y, and these two are the same. Okay, so you can write it that way. And this is what you did here. So what I did, instead of this guy here, instead of this one, I wrote it as this term on the right hand side. If I do that, then my Jacobian, my gradient of the cost function, is summation over, for that del of p, I replace it with p del of log of p, and that r, I just write it down here. So far so good. And based on the definition of expected value, this is basically the expected value of this, because here I use the probability of this trajectory, right, multiplied by it. So that's the expected value of it. Okay. Now, can we do any better? Because so far we have not really done this part. This is the part that we need to do. And you might say, why did you do this trick here? What was the point? Why did you do that? The reason is this. If you look at P has a bunch of product terms in it. So let me show you. P has a bunch of products. It has pi in it, a product. And I want to convert that product into a summation. So the best thing to do is to take log, right? If I have a bunch of terms like y1, y2, then log of that is going to be natural log of y1 plus natural log of y2. And since now it's a linear relation, I can easily now apply my del to these individual ones. Okay? To convert my product into summation, that is why we use the log trick. So now look here, the log of p, this guy here, because p was a product, but now look, log of p is going to be this guy, this log, and summation of all the other terms that were multiplied together. Okay? So now I want to take a gradient from this. The thing is, this guy here has nothing to do with theta. So when I take the gradient with respect to theta, this has nothing to do with it. Also, the transition probabilities have nothing to do with theta. The only term that has theta is this guy, so only this middle term has theta derivative. So I can say that the gradient of log of p is basically the summation, t goes from 0 to t plus 1 of, I can take this gradient inside and log of the policy function. Okay? So now if I plug in this result of equation 6 back into equation 5 and replace this, this part here, guess what? I can find my gradient. So gradient is going to be the expected value of this summation. Okay, so now this guy can be used in my steepest ascent, which I had down here. But here we're going to do one small modification before we do that, and that is really at each time point t, this r of t, which was going from time 0 to the end, look at it, does not have any meaning for arbitrary t, because this is defined for t of 0. But if this is arbitrary t, we really have to go from time t to the final time, not again from time 0, from previous times of that. So instead of using r of tau, which is for the whole trajectory, we have to replace this term with a corresponding one which only goes from time t to the end, with all of these discounted things. And if I call that r sub t instead of r of tau and replace it right here, now my gradient is going to be this guy. That's the same thing as the top. R of tau is replaced with r of t. There we go. So now equation 8 is ready to be directly applied into equation 9. Okay, and that is exactly what you have. This is exactly that gradient that you have. It is going to come right here, multiplied by a learning rate added to the previous value and get you the new value. So this is exactly what you need to do, and that is the reinforce algorithm. Now, one thing we have not discussed so far is, what is this? What would you pick as the policy? Okay, because you have to take log of that, you have to take a gradient of that, and that is going to be your update. So the important thing is, what function would you pick for your policy? And this is our next topic. So here, to define a function for the policy, one of the most common functions that is used, and it's used in reinforce, is called the softmax function. If you watch my videos from the deep learning series, you know that softmax is a function that is used a lot in neural networks, in classification as the last layer of the classification neural networks. So it can give you a probability, right? It gives you a distribution as the output. And so instead of giving you a fixed answer, let's say, you're trying to identify this new image that you have is from which one of these 10 classes. Instead of telling you that, hey, this is class 2, it gives you a probability. It says, well, I give you 10 numbers with like 0.001 out of 1, right? 1% chance is class 1, with like 0.005 is class 2, with like 0.75%, right? 75% is class 3, and then like again 0.001, class 4, all the way to class 10. And then sum of all these numbers equals 1. So basically it gives you is like a probability distribution, okay? And that function, if you remember in these the video I had, or the video I had, which was called the terminologies of machine learning. Let me show you that, which is again under my playlist machine learning. The softmax function was introduced, and this is absolutely a critical function in lots of machine learning. I guess we can see that here, right? So you should be able to find something like that, machine learning language prereqs here, right? Or if you don't like it, you can go to, as I said, my deep learning system playlist. And then here there is one that I have talks about different functions and everything, and classifications, right? Multi-class classifications. And you see again, you have the softmax function. So I have softmax function in lots of different places, and I explained that significantly, okay? So it says basically if you have numbers like z1 all the way to zn, then you can convert them to e to the zi over summation of e to the zi. Okay, so if you go from zi to this new number yi, this yi is first of all between 0 to 1, and sum of them equals 1. So this number is, as I said, the probability. And this is what exactly we're going to use in reinforce. So as you can see here, each theta is, you see that it's the exponential of each theta over summation of the exponentials. So that is exactly a softmax function that you are using in reinforce. Good. Now, let's talk about this function a little bit here, and about this theta of s given a. What is this? This is very important that we clarify this. So if we have a number of states, whatever it is, n sub s of states and n sub a of actions in general for a discrete state, let's say, we can form a table like you have seen in my previous videos where we did a navigation, right, on a grid or something. And then we can have, for instance, each row for one state, each column for an action. And then it says that here, to each one of these cells, which is one pair of S and A, you can allocate a theta. So this one is going to be theta of S1 and A1. This is going to be theta of S3 and A2, right? This is going to be something else. So for each one of these pairs of S and A, you can allocate a theta, right? So you have number of states times number of actions, theta parameters. Good. Now, the question is this. What is this theta really representing here? Remember, this was the parameter that you can change in each policy. The question is, what is the meaning of this theta? And how would you determine that? How would you update it? How would you change it? The big thing is this. Each theta is how much the policy likes to take the action A in probability S. Okay, so that is like the probability of taking A in state S. This theta is basically a representation of that probability. Okay, so all of those numbers are clearly less than 1. And at each state, all of the, like in this case, all of the 4 or 5 actions, some of them should be equal to 1. Okay, so thetas are the likelihood of taking action A in state S for any pair of A and S. Now, they are not exactly, they are basically not exactly probabilities. These thetas are like scores, so they are not directly probabilities, these thetas that you pick. If I show you a theta table, right, which you'll see later, they are not going to be some of them equal to 1 for a specific state or anything. They are just scores. But the thing is, by plugging them into the softmax function, I will turn them into a probability. So although these are just scores, through the softmax function, I turn them now into a real probability. Okay, so this is not exactly this, but output of the softmax function, pi, is exactly a probability, and that is what we want, right? So the policy, I can say that it would select the actions via the softmax function over these parameters. So you pass the parameters to the softmax function, and that is going to be your policy. Now, to give you an idea just with numbers, let's say, for instance, you are in a specific state, state number 7. And at this state, you have basically 4 values for the thetas. Okay, so you have 4 theta values at the state 7. So you came down here to state 7, and you have 4 actions moving up, down, left, and right. So for these 4 actions that you have, the numbers in the table, the theta numbers, are these. Okay, so this is like theta of S equal 7 and action equal 1. Then you have theta of S equal 7 and action equal 2, all the way to 4. So you can write them something like this. Now, if I pass them to the softmax function, so take exponential of them and divide by some exponential, then the policy of taking action 1 under state 7 is going to be like 0.62. For action 2 is going to be 0.17, action 3 0.03, and action 4 is 0.18. Look here, some of these 4 numbers were not equal to 1. But now look at some of these 4 numbers. Is that equal to 1? And you see the answer is yes. Okay, so I could convert those raw scores of theta into a probability, and that can be done for any state. Good? Yep. So in this case, if I say at state 7, which one of the actions is the most likely to be taken, you look at these numbers and say, well, look here, that's the winner. Action number 1 is clearly the winner. Yeah, you could have looked at these as well. You could have looked at these numbers and say, hey, 2 is bigger than the other, so it is 2 that should be taken. But again, we convert them to probabilities, so we can do it completely in a probabilistic framework. And we look at this number, clearly the number that is the biggest, its a softmax function output is also the biggest. So yes, that's the action I'm going to take, action number 1, whatever that action is. Good. So if my policy function is the softmax function, now let's go ahead and plug it up here, take a log of it, take a gradient of it, and see what happens to my update equation for the steepest ascent. So here we go. This is my policy function. Now here we use some notations to make those operations I just mentioned a little bit simpler. So at any action, at any state, the value of the policy for a specific action, like these 4 numbers that I showed you, that is what we showed with pi I. And the value of theta at state S for a specific I, we call it theta I, right? So theta 1, in this case, theta 2, theta 3, theta 4 are these numbers, and these output pi's are, we call them, like in this case, right? So pi 1, pi 2, pi 3, and pi 4. And as I said, we call those guys theta 1 and theta 2 and theta 3 and theta 4. Okay, so we use some notations here. Now, what we do is, what we want to calculate for each one of those individual pi's, we want to take their logs and we want to take their derivative with respect to the theta, correct? That's what we want to do. How do we do it? Well, let's go ahead and see. First thing is, what's the log here? So if I plug in a I here and make this pi I, what's the log of that? Well, clearly the log of this here, right? Because this is a division, and you know log of A over B is going to be log of A minus log of B. And log of exponential is just going to be the theta itself minus and log of the denominator, which you have over here, log of some of the exponentials. Okay? Now, from this log pi that I found, I'm going to take theta derivative. So I take theta derivative of this and this with respect to arbitrary theta j. Now, this first term here is partial of theta I with respect to theta j. Clearly, if I and j are equal, the answer is 1. If they are not equal, that's 0. So here I can show this first part by a delta ij function, which is 1 for I equal j, otherwise it's 0. Yes? And then, what is the derivative of log of the exponential? You know that the derivative of log of anything is basically that entity itself divided by, or the derivative of that entity divided by itself, correct? So we just know that d over dx, we just had it, natural log of y is dy over dx over y itself. So here your y is this summation, right? So it appears in the denominator, and then the derivative of the, in this case, we have to take the derivative of an exponential, and derivative of exponential is just the exponential itself. So it's going to be this one. And if you look at this guy here, that's exactly the definition of the pi itself, right? So if you look at this definition, that is exactly the pi itself. That's the policy, this one. So I can write it as delta ij minus the policy at j. And this is what I was looking for. So this is the answer. Delta ij minus pi j for specific theta j. But when I take a gradient, there is not a single theta j, there are lots of theta j's, right? All of the thetas gonna be there. So instead of writing it individually for any j like this, I can write it as an entire vector. I can write it as a matrix basically for each and every one of the thetas. That will make this delta ij to be written as ei where EI is basically the same as delta IJ, but it is, so if you pick the specific action, it's 1. For other actions, it's 0. So we can say that's the one hot encoding vector, which is basically what this one is. And then this policy pi j, in this case, because you do it for all of the thetas, it is going to be, or you're doing it for all of the actions, I'm sorry, you're doing it for all of the actions, right? Each j is for a specific action, right? Let's go back here. Then you put all of these individual ones in a big vector like this, and you call it the full probability vector, and you see this is basically the vector formed by all of these individual actions. Pi of dot given S, or all of the actions given S for a specific action. And you can write it this way. So if you use the policy function, then that is the gradient that you needed in your update equation here. This term that was the ambiguous one, this guy here, it is EI minus that pi of dot given S under theta. And if you plug that one in, guess what? The final update rule that you will get is actually your reinforce algorithm. Okay, I know it was a lot of math and a lot of proof and everything, but this is basically how it is. So if you want to write a code for this, you have to initialize your thetas, right? And then each time for each episode that you do a training, what you need to do, starting from your initial state, you generate a trajectory under those thetas. Remember, each theta will lead to this pi using the Softmax function. And that will tell you at each state which one of them is the maximum. So you follow that action, it would give you the new state, and you keep going until the end, wherever you end, and then that will give you a trajectory, correct? So that will give you a trajectory. So you have to simulate it all the way to the end. You have to do the whole simulation to the end. And once you have it and you get all of the individual rewards, then you discount them, add them together, and get your R of t. Once you have your R of t here, then you also calculate these guys, right? And you also need to pick your learning rate, and starting from initial theta, you keep updating theta until it does converge. Now here, to show you an example, I have a 10 by 10 grid, and in this 10 by 10 grid, what I did was I can start from any point that I want, but my goal is to reach to the point 10 and 10. So this is where I should end. Now I can start at 1, 1, 1, 2, wherever, right? This is supposed to give me the best policy for any start point. From wherever I start, this should lead me the way. And I have a bunch of cells that are blocked and there are obstacles in them. So the code that I have over here is basically doing this task. It shows you the learn policy. And one of the things you want to do with reinforce is let it go through lots of episodes. If you don't give it enough episode, this method, because it's a simple gradient ascent, is what we call a vanilla gradient ascent, it might not necessarily converge, especially if you don't schedule the learning rate. So this is a simple optimization technique, okay? It cannot handle all of the local maximas and everything. So make sure you give it lots of data and let it run for so many episodes. Don't give it a big learning rate so it doesn't do big oscillations, and hopefully it can converge to something reasonable. And in general, there are more advanced versions of the reinforce that they do regularization, they add entropy terms and so many other things, and we'll talk about that. Okay, in my next video, we're going to talk about A square C, or actor critic. And this one here, this method and the previous methods that we've seen are combined into one to give you the best results. So here we're going to run this, and you can see that every 1,000 episodes, it shows that it has made some progress, and ultimately it shows you a learn policy here. And here I have a sample of that. Now the result that you get is different from time to time. So if you run it now and run it 5 minutes from now, the results are not going to be exactly the same, okay? Because you have not covered all possible scenarios for going from anywhere to the goal. If you want to simulate all possible scenarios, you know how many different episodes you have to give it. And again, it doesn't guarantee that you still can explore it, because not all of them will cover all of these different paths that you can possibly have. So here you're just subsampling all of possible scenarios. And so your policy is going to be basically, hopefully, a good policy. So let's say if I start here from house 1, then I come down here, then I go there, then I go there, here, 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 go down here, go down, go down, go down, and this. Okay, so this is going to be the path that I will take if I follow in house 1, right? Or if I start here, again, you see I go like this. Or actually, in this case, I go, let me clean this. So in this case, I go like this. Right? If I start here, for instance, I go like this. If I start here, I directly go like that. Right? If I start here, I go like this, go down, 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 and then again this. So this is basically what it has learned, and it is going to show it to you at the end. Now, again, my recommendation is give it a lot of episodes. So for the last thing we need to discuss is the advantages and disadvantages of this algorithm. First of all, it's very simple to understand. It's simple gradient ascent, and it directly optimizes the policy, so you don't need to learn any value function. It's naturally all probabilistic. You don't need to know any transition model of the system, so it's model free. It can work with discrete and continuous states, and under some condition, it can guarantee asymptotic convergence. Here I added for you the conditions that you need for the convergence of it. Initially, I didn't want to talk about them, but then I said the lecture is not going to be complete. So one of the most important thing about it is that the policy function that you pick is continuously differentiable, and the gradient be well defined and bounded. And that is why we picked this in this algorithm, not me, I mean the person who developed it, right? His name, I guess, was Williams in 1992. They picked this function because this function not only acts like a probability, it is also between 0 and 1, and the most important, this is a continuously differentiable function, and it has a bounded derivative. So this is a very good common function. The other thing is the estimate that you have from the gradient of the cost function should not be biased. Many times this estimate that we calculate here, this expected value, is actually biased, and that is where in some of the algorithms you see that they subtract some baseline or some bias when they calculate this gradient. And I don't want to get into that right now, but there is that condition as well. For the learning rate, remember this condition we discussed, that the alphas should go down. So, right, remember we talked about this condition, right? We had it in one of our previous videos. That was, let me show you if you want to refer back to it. let's see. There we go. So it was called the Robbins-Monroe conditions. Okay. So here you have to have the same condition for the learning rate to make sure that it works. And then going back, the variance of this gradient, because this gradient is just a probabilistic number also, so it might be biased, but also it has variance. We need to make sure that the variance of it is also finite. Sometimes the variance of this estimate can grow very large. And if it goes very large, your algorithm might actually not converge, or it goes very slowly. The other thing is you might explore the state action space sufficiently to make sure you're not stuck in any local maxima, okay? Then make sure that the rewards that you define in your state action space, they are bounded, okay? And typically you don't want them to be super sparse as well, because if they are sparse, you're not giving it enough direction for where to go. And finally, the Markov decision process that you have behind this says that your environment has to be stationary and your transitions and rewards should not change over time. If you have all of those, then you can get some asymptotic convergence. What are the disadvantages is, as I said, sometimes the gradient estimate could have big variances because you need, remember I told you, give it a lot of episodes so you get some good estimates. That makes it sample inefficient. So you need to run so many episodes to learn. This clearly does not do bootstrapping. As I said, you have to let your simulation go to the very end to calculate that R of t function. And so this is not going to be in real time. You have to wait for the result to come back. Then you can have poor credit assignments. If you want, we can talk about it we talked a little bit about it, right? About the previous states and so on. It's quite a bit sensitive to the hyperparameters, especially alpha and to some extent gamma. And as I said, there is no learning during the episode. You have to wait as a Monte Carlo approach to bring your R theta back. So it has delayed updates. Okay. But as I said, I'm going to give you this code under video description so you can download it and play with it. And hopefully you learn at least one of the most common baseline methods of policy base in reinforcement learning, which is called reinforce itself, right? You learn how this is working. You learn behind the scene a little bit, why we pick the policy function as a softmax function and so on, and learn about the advantages and disadvantages. So thank you so much. I'll see you in the next lecture.